So this will be modeling cores. I think this title of this section is a bit incorrect, because really, what we're really going to cover is how to implement ISA instructions and how we model those in gem5, not necessarily the entirety of the cores. This is what this session is going to be focused on. There will be some coding examples, and I will put this giant disclaimer over this kind of whole section. I would say no one fully understands how end-to-end ISAs are implemented in gem5. There's giant pieces of very complex code involved, and I'm only going to focus in on a few parts. It is incredibly complex, but I'm going to give you hopefully enough information to do this yourself. But it is an extremely complex part of the code base, and I think it, in some cases, has got a bit unwieldy, and you kind of have to dive in and just look through the spaghetti code yourself to figure out what's going on. But I think this session should give you a decent enough overview to implement your own instructions or your own ISAs if you so see fit. So go over what is an ISA, structured architecture. It defines the instructions a processor can execute, the registers that are available, the memory model, and the exception and interrupt handling. And that's basically what we're going to focus on implementing and going over implementing inside gem5. For this tutorial, we're going to focus on the vis5 instruction set architecture. But almost everything I explained here is applicable to the other gem5 ISAs or whatever you want. I just focus on vis5 because it's probably the best, it's one of the 3 most mature ISAs, and it's open source, so we might as well go in with it. And this is I'm going to go over this. So in gem5, we can simulate the ARM ISA, the vis5 ISA, x86, NIPS, and Spark. But realistically, you can probably only use, you'll probably only use ARM, vis5, and x86. The remainder of those are implemented, not very well tested, and I can say as someone who works on a project day to day, not very well maintained. I can't remember the last time anyone pushed any improvements to MIPS or Spark, so use them at your own risk, but they are technically still there. The real kind of innovation and the clever bit of gem5 is the ISA and CPU are completely decoupled concepts. Well, not completely decoupled. They're significantly decoupled concepts inside how we build this. So you can have a CPU model like out of order core and plug in any ISA into that, and you don't have to do any kind of bespoke code. So it means theoretically, if you wanted to add a completely new ISA into gem5, you could use, assuming you do it correctly, all the current core models that are currently there, such as out of order core, for example. It's completely agnostic. You just have to make sure you define certain things in your ISA model, and it works from there. We'll go over this probably in excruciating detail, but our core models in gem5 kind of just see an instruction from any ISA as this kind of instruction object, and it doesn't really care what it's doing. The instruction object defines what that instruction does and how it's executed, how it affects registers, how it affects the memory state, etc. And the CPU model kind of handles that. So I'm just going to use a disclaimer here that really, I would say all you really have to define in your ISA is the decoder. And I use this word very broadly. I'm not really using it in the traditional architectural sense. I'm just saying that the decoder in your ISA, first of all, decodes the stream of bits into an instruction, but also kind of defines what that instruction does. So it kind of also contains the function. Let's say like a copy operation, it'll define how a copy works, say copying from a memory location to another memory location. So I use it in a very broad sense, but essentially the way this kind of works at a high level is for the ISA, you define the decoder, and then when you implement it in gem5 and you create your, let's say, x86 core, the x86 decoder is plugged into the core model, and that's how that kind of works. So You probably are going to struggle to read this because there's a lot of information here, but this is essentially a diagram I stole from the last time I had a boot camp because it's quite good. I won't go over everything in this in detail, but it goes over the various parts that are ISA independent or the CPU independent. But I think the key thing here is you implement the decoder at the top based on ISA description, and through all this, other things are kind of inferred or derived from it, in particular the static instructions, which we're going to go over in a bit. And yeah, this is way a bit too detailed for the level I'm going to go into, but you can refer to this if you're diving into the CPU and want to see what parts are used in what stages of the decoding and the processing of the instruction. I really think the core part of understanding this is you have an ISA description, and from that you can get a decoder, and you plug in the decoder into your CPU, and that's how you create a x86 or RISC-V or ARM CPU model, and from there on gem5 you can process instructions simulating a real-world piece of hardware. So I think this is the important part here. Regardless of the ISA created, parses an instruction received by the CPU into a static instruction object. A static instruction is an object containing static information about a particular ISA instruction for all instances of that instruction. It contains information on the operation class, the source and destination registers, flags to show if the instruction has micro-ops, functions defining the instruction's behavior, very important. So from that, in that static instruction, there is a function that will essentially define what that instruction does and is therefore called by the processor to carry out that instruction's behavior. Oh yeah, there. We're going to go over these more in later slides. So you will, in every static instruction, you have defined execute, initiate access, complete access, and disassemble. So these are what the processor calls to execute that instruction at particular points. The processor will decide when these are called. Sorry, the CPU will decide when these are called, but those define the behavior. There's also dynamic instructions. Objects contains information that is specific to a particular instance of that instruction. They are constructed from information in the static instruction objects, and they contain information on PC and predicted next PC, instruction result, thread number, CPU, and renamed register indices. Oh, and they also provide exec context interface. This is, yeah, no, the exec context interface is kind of important. The exec context interface provides methods in which an instruction may interface with a CPU model in a standardized way, and dynamic instruction objects implement the exec context interface. This is getting a little bit convoluted. It's okay if you're a bit confused here. We're going to go over this in a few examples. But I think the important thing is when an instruction is received from the CPU, it is decoded into a static instruction. And from there, there's kind of a chain of events you can do to eventually execute your instruction in a standardized way that is completely ISA agnostic, because every ISA instruction received by the processor can be cast into the static instruction object, which provides a standardized interface to process these instructions. So I'm going to go through a little example here. In this example, we're going to use the JDB trace, JDB to trace the execution of an instruction in gem5. So I will jump to my slide, to my thing here. I find it's very handy to have this to the side here. So if you go to Materials, O3, Developing Gem5, O5, Modeling Cores, and get yourself in that directory in the terminal. So I'm going to do here. Materials, O3, O5, O1 inst. Oh, wait, sorry, I don't want to jump quickly there. So what I'm going to do is, first of all, GDB our gem5 binary here. I think sure hooks. Nice. I'm gonna make this a little bigger. What's the thing? Let's wait for it to read the symbols. And what we're going to do is add breakpoints at specific instructions. So the first thing we're going to do is we're going to focus on the add instruction. And what we're going to do is, and then by the way, this is, I don't think I said to this point, but this is going to be in the RISC-V ISA here. So we want to do add, which is just the, we're going to add a breakpoint. Add. And that's just the construction for that static instruction for the add instruction. I'm using the word instruction too much, but yes. So this is the constructor. We want to see where inside a particular execution of gem5 this instruction is constructed. This is just adding the breakpoint. We're not executing anything yet. No. And then another breakpoint for add execute function. So in this instance, we're saying I want to see where this instruction is executed inside a particular run of gem5. So I just want to add a breakpoint on that function. Nice. And then we're going to run a particular example here. I suppose I'll show you briefly what this does. If I go to materials, no. So this is doing a very, very simple execution of gem5. It's running. It's really literally running a hello world example here on a simple SE workload using a timing core, one core, RISC-V ISA. It's a very, very simple execution. So what I'm going to do is run O1 inst trace. Starting here, we should run right up until our first breakpoint. Cool, we've reached the breakpoint here. It says, hey, I've reached this breakpoint, gem5, RISC-V ISA instruction, add. So what I want to do here is get the backtrace. Backtrace will get all the functions that have been called to get to that function call. Sure, I think you can write backtrace fully, but I just do BT and then 10. That specifies how many calls back do we want to see. I want to see what the last 10 functions calls to get to that add construction. And I'll get this. Nope. So you can see here, 0 to 9, the zeroth function here is the actual add, and we can see the various functions we need to call to get to this point. I'm going to just one second, let's see. So I would say, if you kind of look through this, number 5 here is when we kind of start to see things interesting. From 6 onwards, it's really just the simulation loop, do sim loop, and executing something off the event queue. By number 5, we do this complete ifetch instruction, and then we do a pre-execute, decode, another decode, a decode instruction, and eventually we construct this add. So let's kind of see what's happening here. If we jump into source, so if we let's try to find this pre-execute function and see what's actually happening here. I'm trying to find my slides again. Come on. Okay, there we go. So we go to source, CPU, simple, base. We'll find this. So I'm going to go here, source, CPU, simple, base CC, and just going to do Control F to find this pre-execute. And this is the function that has been called, a number at the here, and the here is here in the backtrace. And from here we should, so this is pre-execute is, as you might imagine, what the CPU calls before it begins executing an instruction. So it does a lot of kind of housekeeping tasks, resets predicate, and then does various things to actually jump into decoding the instruction, which I'm about to go into. And I think that's all. Yeah, it does some various things here as well. But I'm not really going to concern myself with this. This is just trying to find the flow of things and how this instruction is eventually executed. Important thing here is to see from the decoder here, you eventually run the decode example, and so I believe if you go down, it should be, I think it is this one. So I should have taken better notes here to see what we're supposed to be looking at. 4, 3. Oh yeah, here's so from the pre-execute, you eventually reach this stage here. It's saying decode, and eventually jumps into various decode instructions. As you can see, this decode exists at source, RISC-V decoder, so we can jump there, arch, RISC-V decoder, go to the same thing, just trying to find it. So this, and I'm going to skip these next few things in the backtrace because they are just jumping through a series of the codes that are actually kind of basically wrappers for the main event. Because the main event here is, you can see at number 2, gem5 RISC-V ISC decoder decode. And sorry. Oh, okay, never mind. Slides aren't. So this is where it gets a little bit complicated, because eventually we reach this generated code here. Now, if you haven't built gem5 yet, you won't have these on your system from these built sources, but I have provided them. If you go to, I have provided them just as a copy. If you go to materials and O3 modeling cores, I provide these generated files here. So eventually you go through the CPU model, and eventually you hit this generated code. And here it is decode method.cc.inc. And this is generated C++ code. I'm going to explain how these are generated. But for our intents and purposes, I believe this should be according to my thing at line 2743. 2743. You can see how big this generated file is. Kind of scary. Yep, so here is the add construction. So this is saying add, and you're taking a particular machine instruction here. And this is essentially how the CPU arrives at this construction. So what's going on here? This here is a giant decode operation which works inside a giant switch statement, which is really hard to navigate because it's generated code. It's not really designed to be necessarily human readable. And we'll explain this in a bit, but this is essentially a giant switch statement that will eventually get you to the instruction, to the decoded instruction from a particular bit stream, essentially, that arrives at the CPU. It's confusing, but we're going to go over a couple more examples. Hopefully this concept becomes a little bit more better ingrained. I'm going to quickly go back to this laptop and find my references. So I think it helps. I've kind of provided here on the slides. Here's kind of the snippet of all this. I've removed everything that all the switch parts that aren't to do with directly the add instruction. Essentially, you start off here. Yeah, you start off at the case and some hex here. Switch, 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 until eventually you get to this add construction here. You break. And we're going to show what this essentially means, but in short, in short, you're essentially saying, these are parts of the instruction you are decoding. You're saying if the func t of this particular instruction is of value 0, and the funct5 is of value 0, and the bs of value 0, that it must be an add instruction. Let's construct our add instruction here. And yes, here it's in this particularly hard to read language. Let's continue and do the same for execute. So remember, we created a breakpoint for execute. You can just type C here, which is C for continue on this debugging process. We're saying let's move on from this add and see what happens when this add is eventually executed. Yep, we've reached it. And let's do a backtrace to 5 here to see what's happened. There. So as you see, there's let's see. Here's where it's executed. It's executed in this generated piece of code here. And here at source, CPU simple timing at line 876, this is called. So let's jump in there. Let's go back. I believe we already have this open somewhere. Maybe not. Source. Simple timing. (876). Oh. So yep, this is where the instruction ultimately executed. You see there's this big kind of piece of logic here. All this is essentially, and we're going to go back to this in a bit briefly, but it's saying, hey, we've got this static instruction, let's execute it. We're in this function here called complete I fetch. So we fetch this instruction and we're going to just execute it immediately. I'm going to go over the various pieces of logic that are going on in this function here. Here we execute it, and we're executing it in this generated file here. So again, this is generated during compilation, but I provided it with you inside the materials. EXX ns.cc.inst, and line 27.371. So we go back to materials. Here. Let's go all the way down. One. I sure hope this is right. 27.361. Huh. Maybe. Okay, when in doubt. Yep. Yeah. Okay. Is that the compressed version? This one? Yeah. So here is the actual, sorry, I'm here. Here's the actual execute function is executed from the generated code. This is generated C++ code. This is C++. It's just not formatted very nicely. It's got all these like random semicolons and thing. You can take your time to like, you can format this if you want to make it easier, like if you wish. But I think you get the general kind of thing here. This is doing a bunch of register operations. So this is saying get register 1, get register 2, do an operation here, add these two, this is add operation, so add these two registers together, put it in register RED, or the RED's value, and then set the register value here, and then set the register, here, and then provide a trace, and then return a fault if there is one, which there isn't, there's just no fault. There. It's a very simple add operation. Destination register here, RD, two source registers, R1 and RS. You fill up the two source registers, you calculate the the value of them two added together, and then you set the destination register. And all these things are inferred by the execution context. The properties of these registers is found through the execution context. If you remember, the execution context is the kind of bridge between instructions and the CPU model. So when passed here, the execution context allows the instruction to get things like get this register and set the registers. And this is like a standardized interface between the two. So yeah. This way a simple operation as you can probably get add addition of two registers together. So any kind of questions at this point, you should probably feel confused because this is kind of confusing parts of the code. So I've been focusing on this idea that you get a static instruction and you call execute, which has been a little bit misleading because not all of the instructions work exactly this way. There's really it really does depend on various things whether this execute function is called. And in short, the execute on the static instruction is called in this case because this is a non-memory operation. We don't need to model any memory accesses for this operation to work. And therefore, execute essentially runs the instruction from a simulation point of view instantaneously. So an instructions execute function is called when you literally want the entire operation of that instruction to be executed from a simulation point of view instantaneously, which is okay if you're not modeling any memory accesses because that's a decent simulation, i.e. in this case, this add function adds two registers together. Well, there's no memory access. We can probably model that as being an instantaneous operation, i.e. this operation happens in one tick and no additional time was taken. But in other cases, we don't want to do it this way. We want to model memory accesses. There's plenty of instructions out there that will require the fetching of a particular memory location or require that to be returned to then complete the operation of that instruction. And that takes time, which we want to model inside gem5 in order to get accurate results. So the static instruction has three operations, three functions that we actually care about, used to execute the instruction. Execute, which you just discussed. Execute will execute the instruction instantaneously, like that. The moment you call execute, all the registers magically become what the values they're supposed to be, which is great, but not really good if you want to simulate realistic timing of memory accesses, etc. If we want to model memory accesses, we have to use initiate access. It's used to initiate the memory system access. Use to initiate a memory access through the memory system. It does everything right up to the actual execution of the instruction. The memory system will then call, complete access to complete the access and trigger the execution of the instruction. It's kind of a two-part process. The latter two instructions are used, so the initiate access and the complete access are used for memory instructions such as timed memory access mode when the instruction is a memory instruction, i.e. loads memory, and therefore timing information is needed. If you remember, there's two kind of broad memory access modes in gem5, timing and atomic. In atomic mode, we only really use exec because atomic mode doesn't care about modeling memory access behavior. If we're in timing mode, it's kind of, you can see there's a kind of a, in timing mode, we do model the memory access information. So in cases where we've got a memory instruction, the initiate access and complete access is used. And here, this might be a bit small for you. I'll see if it's slightly bigger. Otherwise, you can use your own slides here. Jason, do you have a comment? Okay, sorry, I've got very, so this is a kind of flow diagram I made before that you kind of think of how this is done. You got your two kind of memory access modes in gem5. If you're in atomic, the CPU runs pre-execute, the instructions execute function is called, and then the CPU executes post-execute. Very, very simple process. And that middle part there, execute, is, well, all of that is like in a single tick. This all happens instantaneously. We're not modeling anything. From the simulation point of view, the instruction has went beyond the speed of light and is just there magically in one single moment. The timing memory access model is a little more different. If it's not a memory, if it has not a memory operation, i.e. it doesn't reference anything in memory, it is pretty much like the atomic memory access. You pre-execute, you run the instruction execute, the CPU runs post-execute, all in one tick. If it isn't, a little bit more complicated, the instructions initiate access function is called. The CPU therefore calls initiate mem read, which calls the memory system, and the memory system then schedules an event at some point in the future, dependent on how it models timing. So, i.e., there's a latency to trigger the CPU's receive timing request. So, at some point in the future, that you have received your timing request. When that event happens, the CPU's iCache instruction runs complete access, which therefore kind of properly executes the remainder of the instruction, and then CPU runs post-execute. So this sort of bottom left corner here, the initiate memory read access and the receive timing request, because you are scheduling events on the event queue there, that's how we simulate the timing of the receiving of that memory operation and how therefore model how an instruction how an instruction executed can take time from a simulation point of view, which is important because that's essentially what we're using gem5 for in many cases. So far we've seen how an instruction is decoded, then executed in gem5. However, we haven't seen how this decoding process is defined, which is kind of an important thing if you want to actually implement your own instruction. And the behavior of instructions execution is defined. So we've seen that there's kind of two modes of operation for an instruction, either execute or initiate access, and then so forth. And here we're going to see how this is defined. So if you go to the source arch, in this case RISC-V ISA directory, you can see how you can see the ISA definition. This is the part that I really don't like, but it's written in its own language that's not really defined anywhere, which we call the ISA domain-specific language, or the ISA DSL. And this language is interpreted by what we call the ISA parser, which is just a Python script, which you can find there at the source arch ISA parser directory. And then that generates C++ code, and that C++ code is then compiled just in the standard way and linked into the gem5 binary as any other C++ code is. That C++ code is what we saw before when I was going through that 100,000 line file. That's what's generated. It is generated C++ code, and it is just compiled into the gem5 binary. So before I jump into kind of going through some examples here, I want you to get over the important high-level ideas first, because I think you can get really lost in this. You can get really lost in how the ISA parser parses everything and how the decoder actually works. But the high level, you have these .isa files, which again are written in this bespoke language that we made ourselves at some point. And then the ISA, I don't know why, that second part shouldn't say ISA compiler, it should say ISA parser, sorry. So the ISA files are parsed by the ISA parser, and then you get the decoder and instruction code. And then our actual compiler compiles them into CPU models. Actually, kind of a two-part process here. The compiler will actually compile our CPU models and our RISC-V kind of models, link them together to create things like the RISC-V timing CPU, for example, or the RISC-V atomic CPU. I think the top part is the most important part. The parser will take in these files, create C++ code. Our compiler will then take the C++ code and compile in gem5. So that, I think, is one of the hardest or things you should definitely keep in mind when kind of getting into this, because everything else here is kind of spaghetti code that can really get you lost and confused pretty easily. And I think the painful truth is to add and extend an ISA, most developers will just grep for similar instructions and try to work. Okay, so I'm going to go into some examples here. So I'm going to look at one instruction inside RISC-V and we're going to see how it's decoded and eventually executed inside RISC-V, just to look at the source code and see if we can understand this a bit easier. So, if the instruction we're going to focus on is LW, or load word, which loads a word into our register. So again, it's a pretty simple instruction, but it should give you an idea of how this is all done. The first thing you need to do before you really try to implement or understand an instruction in a particular ISA is to kind of look at the format in which the ISA instruction is defined. And of course, this varies a lot between this varies completely between ISAs. So I'm just going to talk about RISC-V here. So RISC-V has at least I'm going to count there, at least 6 we're going to talk about here. Formats, R, I, S, B, U, and J, and they define how the instruction is defined. And I just copy and pasted this off, I think, the RISC-V website, but this is kind of saying for the R types instructions, the first, first 6 bits defines the func, and then the next 5 defines the R2, and then the RS1, that's a register source 2, register source 1. The other one also defines the function, and then the other 5 define the destination register, and the last 7 there define the opcode. So our challenge here with kind of writing this, kind of simulating this in Gem5 is we have to decode all this as it comes in. So we need to say for a particular instruction that comes in, we need to translate it to a particular instruction, and we need to have defined how that instruction is executed. I'm not going to go over this. These are just the types in RISC-V. So the RISC-V's load word instruction is an I-type instruction, which loads 32-bit value from memory into a register. So this is a memory instruction. If we're using timing mode, we will have to have the initiate access and functions used. This is the definition here. It loads the value of source register 1 into the destination register, RD plus M. If M is 0, the full word, 32 bits of RS1 is loaded into the destination register. If this value is used to load, if it is used, we do a subword. So this gets a bit more complicated here, and it doesn't really matter for the sake of our example. But the IMM is used to load the subword. IMM shifts the bits to the source register 1 prior to loading to RD. So if it's 15, the value RS1 is shifted by 15 bits before being loaded into the source destination. So remember here, it's an I-type instruction. So go back here. We expect there to be an intermediate, a source destination, a function, a source register, destination register. And so we're really, in the I-type instructions, there's kind of, I would say, yeah, we've obviously got the opcode, we've got the destination register and a source register and an intermediate value. We've also got this func value, which also defines the nature of the operation. So we need to read these values in and then discover what instruction we're actually dealing with. Core thing is probably the opcode, but once we understand the opcode, we also have to parse therein the destination register, the source register, and this immediate value here, which is also used to shift bits in our example here. You can see if we were dealing with an R value, we'd also have to parse in and get the second source register. In this case, we don't need to. I-type instructions don't have a second source register. We don't have to deal with that. Yep. So consider the following. Considering our processor core receives this. Well, we kind of parse it down into these sort of 1, 2, 3, 4, 5 chunks here. The immediate, the source register, another func3, and then RD, and then the opcode. So in this example, the register with address 2 is loaded into the register with address 3 with an offset of 1. Func3 is the function code for load word instruction. This is always 0, 0, 1, 0 for the load word instruction. And opcode is the operation code for the L1 instruction, also always the same. Obviously, because if it wasn't the same, it would be a different operation. That's just how the operation is defined and recognized. Note, in general, we additionally refer to quadrant or quad, which is the last 2 bits of the opcode, in this case, 1, 1, and opcode 5, which refers to the opcode bit shift right by 2. So basically opcode without quad, in this case 0, 0, 0. It's a bit confusing, but this is going to come up just in a bit. So we do kind of split the quad, the last two bits here, away from the rest of the opcode to do some parsing, which is part of the RISC-V specification, but I won't go too far into it here. So what the ISA definition does is define how an instruction is decoded by breaking down into the parts, bit fields of the instruction. And if you go into, I'll go into it here briefly, source, architecture, RISC-V, ISA, bit fields. Source, arch, RISC-V, ISA, bit fields here. You can kind of see this broken down. So we've got this quadrant saying, hey, that's the bits 0 to 1, opcode 5, that's bits 2 to 6. And we're going to go to, let's go down to, you got all these, what were we type I can't quite remember. Or you can see for the R type here, it's saying, okay, all the bits are bits 0 to 31, that's the entire 32-bit range. And then we're kind of defining sub-bits here, saying, hey, this is func3. Func3 is bits 12 to 14. And the first source register is bits 15 to 19. And for the I type, it's bits 20 to 31. So this is various ways of breaking up the input. So we completely use these to, we have the 32-bit come in, and we get all the bit field information here. Just basically sub-bit fields and how they're defined. Where the magic happens is if you go into decoder.isa and search for LW, you'll find something that looks like this. So the following defines, again, I've kind of taken away almost this is much more verbose inside the decoder.isa, but I've removed almost all the code that has nothing to do with the actual LW operation here. But you can kind of go through this and kind of see a certain logic. It's saying here, decode quadrant, and then here, the second kind of line, this part, saying, if the quadrant is 0x3, this is like hexadecimal, then decode opcode 5, and if that value is 0 in hex, then decode func3, format load. I'm just going to brush over that briefly right now, but that's kind of like a wrapper. But if func3 is 2, then we must be a load word, and in which case, this is basically loading. So it's just saying the destination register equals this memory location. I'm going to go over this kind of language we use here, but that's just defining what the instruction does. And that's how we reach our destination. So we kind of break down the instruction into these chunks, and we do this kind of branching logic here to eventually arrive at the instruction we want. This format here is defining the format of the code that should be generated. So we've got a format called load that basically will understand what this means and create the C++ code we need. Going over that in, I think, 1 or 2 slides. But I'll continue with the kind of decoder part of this operation. Again, think about the language here. I read this as, so if quadrant equals x 003, then decode opcode 5. If opcode 5 is 0, then decode func3. And if func3 is 2, then we declare the LW instruction, which is this. That's how we define the decoding of an instruction. I'm going to go over how this decoder is generated. So if you remember correctly, this is all our bespoke ISA instruction declaration language. And the ISA parser will take in this decoder and create C++ code. So that top line there, like decode quadrant, default unknown, that is parsed into C++ into this. RISC-V, decoder, decode, switch quadrant. 3 decode opcode 5 becomes this. We're saying, hey, in the case, this is 03, switch, opcode 5. Similar story here. And finally this. So the complete translation becomes this. It's just a series of switch statements, which is actually quite simple. And I hope you kind of see how this kind of all fits together. I'm going to jump back to just so you can see this actually in the code. So what I do here when I want to find something is I just Control F. I don't think there's really, I Control F for LW. Nope, 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 nope. Yep, there it is. There's the LW operation. Again, in my slides, I've removed a lot of this other stuff that isn't relevant. See, oh, L2 is decoding func3 00, which is of opcode 5 00 3. And you can scroll all the way up here to find where that decode opcode here, the code quadrant. Yeah, so this is a part that is kind of we maintain and define how the decoder works here. And that is parsed into, go back to remember. This giant file here, which again is really just a series of switch statements. And these funct3 things are defined again inside the bit fields.ini inside where we define our ISA. So any questions about that point? I think this is, yeah. I'm going to move on to less so about how it's decoded and more so how the instruction's execution is defined. Okay. So if you actually, so I brushed over this whole load thing here. And this is where I think everything does become very messy, and I can't give you straight generic answers for everything. This load format is essentially a template of how this instruction is defined. And inside our ISA definition, there is a template called load. It's just, at some point, someone decided that a lot of operations load things from memory to certain places, and therefore they created a template for this that essentially understands what this means, and then uses it, translates it, and loads it to create some C++ code. So I will attempt to show some of this, if I can. So I'm going to go to the generated stuff here. I'm going to search for, I'm going to try to find LW inside this generated code. And it might take some time. Yep, so there's our load instruction inside the generated C++. construction here. And as you remember, so this is just the construct thing. If we go into the exact G, I want to say, maybe not, nope, not there, exact, no, NS. I literally just scroll left through this until I wish always didn't appear so much here. Yep. So somehow we get from that load format template to get this, which it defines our execution, load, and here's our initiate access information, and there's our complete access. So how do we get from there to there? Say, jump here. So all these templates in here, I'm pretty sure if I, so we want to load. Oh, great, it's not there. Where is it again? Formats. I'm just going to try to do, so honestly, one of my favorite things, and I use that completely sarcastically, is to try to find out where formats are defined inside the ISA definition. And I find sometimes the best way is just to grep the entire directory for the keyword you're looking for, because it is very hard to find sometimes. So I'm going to go back, I'm going to go way back to gem5, source, arch, gem5, ISA, and grep for load. I'm sure I'm going to hit tons here. Huh, where is it then? Is it in ISA parser? Oops. Okay, I'm going to call that part of my presentation a dud because I can't even find the function that I was supposed to be referring to. Oh, it's because, is it because I was using capital? 1 second, I'm just going to check. I'm not doing capital, not capital L. Oh, there, okay. Yep, case sensitive, of course. I want to find. Yeah, so format load is in decoder ISA at line 531. Yep, so here's, that's not what I wanted exactly. Where's this defined? Def, I wanted to go for. So, yep. Templates. We have all these various loads. So formats. Oh. So I can't find exactly what I'm trying to find here. I don't want to waste too much time jumping around using grep. But this is a good example of a template here. It's just, you can see all these percentage signs, class name, percentage sign, class name, percentage sign op declaration, percentage sign op RA. And this is all just like placeholders for C++ code that's defined elsewhere. You can see there's this like C++ code here, and then some other placeholder here, and eventually return no fault. And if you look around enough, you can see where this is defined. So this, I think you might be in this file somewhere, maybe not. Yep, this is loaded in from this function here, so you would eventually call this. I don't want to get too much into detail here because I could probably go through and find out where everything is defined here and there for hours. Just so you know, this is like a very templatized language that has formats within formats and templates within templates. And that is eventually used to construct your C++ code. So you can see little like, if you go into these files here, you can see how this, a decent example. Like here's an example of a load declaration template, which is just saying loading a store declaration. And this is kind of pseudo C with some placeholders here. And this is how the ISA part, this is what the ISA parser reads in, and it fills in these parts based on what you've declared elsewhere, and eventually creates your C++ code from there. I would broadly say if you're trying to implement your own instruction, try to find an instruction that's broadly similar, and just essentially work from there, because trying to get this done from scratch can be very, very difficult to try to find what you're looking for. As I have proven, stumbling around trying to find even the load template, which I can't fully find right now. It's somewhere in there. Can I jump back to my slides? Oops. I'll leave this more in the slides. I won't jump completely into it. But if you go into this class here, you can see the generated class for the for the load word instruction. It's a little bit more readable than a lot more of for most of the generated code. But you can see here we define our three functions we really care about: execute, initiate access, and complete access. I'll say you can complete exploring this in your own time. The templates are complex and typically build on other templates and specialized translation code inside the ISA parser.script. But analyzing the ISA definition and ISA parser script, you can get a better understanding of how the ISA is defined and how the instructions are decoded and executed. Generated is valid C++ code and can be understood by trying to understand the generated code. Using breakpoints in the GDB to trace the execution of an instruction in gem5 is a good way to understand how the generated code is used and used to decode and execute an instruction. It's like high-level comments if you're trying to do this by yourself. These are good tips when you're trying to dive in and try to understand this. So I'm going to go through an exercise with you. We're going to add an instruction called add16. You can play along or just follow me. Depending on your level of enthusiasm with this, or you can try this in your own free time. The add16 instruction is a 16-bit addition instruction that adds two 16-bit values and stores the result in a 16-bit register. Very similar to what we've seen before, very simple. I'm just going to show you how it's done. We're going to define our format here. So it's a 32-bit instruction. The bits 31, 25 are what we call func7. They're of this value. 0, 1, blah, blah, blah. We've got one source register, and well, two source registers from bits 24 to 15. Then we've got func3, which is always 0, 0, 0. Then we've got the destination register, which is 11 to 6. And then 6 to 0 is our opcode. The syntax is just R16, R1, R2. We should have a destination register in there, but okay. So it's pretty straightforward. We take the values from the two source registers, and we add them together, 16 bits, and add them to the destination register. Pretty simple. So we go to, oh, that didn't work. I'm just gonna have my slides up here side by side a little bit. Oop. Okay. Okay. Materials. All3, all-in cores, all2, add inst. So I've got some test functions here that actually execute execute a binary with this instruction added. You can see the C++ code here. It does some funky business here, but this will essentially ensure that this is basically a test binary that ensures that we've actually implemented this instruction and it works as intended. You don't have to worry about that. I pre-built this here. We don't have enough time to actually build gem5 in this tutorial, so you can try this in your own time. But I'm going to go through and add this instruction, and when you compile gem5 and run this script here, which uses this binary, it should execute completely and give you the thumbs up. Yes, you've successfully added this instruction in gem5. Well done. So if you kind of materials. 5 on the cores. Do 2. Add 16 test.py. This will just fail because it's going to say, hey, we don't have this instruction. Not sure if it actually gives an error as helpful as that. Nope, it just gives this really horrible backtrace. But that's because we haven't implemented the instruction. Gem5 kind of goes, whoa, I don't know this. I don't have this instruction, and kind of just dies. Yep. So let's start at the beginning. What do we want to do here? Well, first we have to define our decoder for this instruction. Let's break this down into our normal kind of things. We've got our quadrant, our opcode 5, our func3, and func7. That's kind of the way our instructions are found. Everything else we can kind of ignore for now because it's not necessarily to do with the coding of the instruction. It's not used to define what our instruction actually is. Those are like the source and destination register information, which we don't need right now. These are the static values we actually need to remember and implement in our decoder. And this is essentially what we want to kind of add. We're saying if the quadrant is 0.3 and the opcode 5 is 1D and the func3 is 0, so here we're just directly lifting these values from here and shoving them into this if statement here. Yeah. I would say just if you can just write this basically on pen and paper in front of you, like when you're trying to implement your instruction, you've done most of the decoding, work that's needing done, and we're kind of ignoring the actual addition of the instruction here. We're going to do that in a bit. In the interest of time, because we've only got 10 minutes until lunch, I won't do this right in front of you, but I hope you can see how you can take kind of this kind of code here, and you just have to squeeze it in, for lack of a better terminology, into source, arch, gem5, ISA, decoder. You need to find where this should be where this should be squeezed in here. Oops. So we already have probably 0.3. Yeah, so the important thing to note here is we already have the other instructions that have the same quadrant opcode values, just different funct3 values. So we have to insert this into the correct place. Ergo, we just need to insert this part into the place it's supposed to go. So we can kind of search our file for, okay, somewhere we've already got a quadrant defined of 3, 3. So we go, I typically go up to the top here. Quadrant, 0, 0, nope. 0, 1, nope, almost there. 0, 2, nope, surely next one. Okay, yep, this is where we want to be, somewhere in here. Okay, yep, and we've got opcode 5 of 1D. Okay, just scroll down, try to find logically where this should go. This doesn't, I don't think this needs to be ordered, but obviously it's nice that it is, so keep them with the style. Say you do this a lot of scrolling until you find out where this logically should be. I'm just going to be lazy and say, oh, screw it, it should be here. And then you just do 1 times 1D. You can just copy and paste in this. We've already done this logic. There, and then all we're left to do is really add the instruction, actually itself. Next, let's add the instruction. Well, this code here, add 16, and then the kind of weird open bracket, 2 curly brackets, and then 2 close curly brackets, close the parenthesis, semicolon. That's just saying, hey, our instruction is called add 16. Still need to fill this part here. Not going to go completely over this because it's complicated. But you see, this is mostly C++ code here. It's basically taking in the source 1 destination register, source 2 destination registers, and doing some bit shift operations here. And then to the destination register. Sorry, I didn't mean to do that. Well, anyway. So to the destination register, we're setting its value, again, using some bit shift operations here. I'm just going to copy and paste this in. And I'm sure there's probably 1 or 2 typos in there. I mean, just from the copy and pasting, or maybe I put this slightly in the wrong place. But that is essentially completely implemented the instruction. So we've really only modified one instruction here, one file here, which is the decoder, 2-step process. 1, define using the actual, what you know of the ISA specification, how this is supposed to be decoded. And then from there, you implement the instruction by defining its name, in this case add 16. And then in here, you define the actual how it's decoded. This is highly dependent on the ISA parser and the various templates involved. Here is actually very simple. It's mostly C++ code, which is pretty good. And then I believe, if I've done everything correctly, I know from the slide, if you look on the slides example is complete. I've tried that many times. It does work. After that, all you need to do is compile gem5. Again, it will take like you 40 minutes or something to actually do. And then if you actually execute gem5 on this add 16 test, it'll go, yeah, test passed. Congratulations, you have implemented this instruction correctly. You can try this in your own time. I thoroughly recommend doing it. It's very satisfying to have say implemented an instruction in gem5. There's plenty of instructions, even in current ISA specification, that haven't been implemented in gem5 if you want to have a go. Or you can just make up your own instruction, have a go. You can keep it as simple as you want. You can even have an instruction that already exists, but just call it something else, a slightly different decode operation. Inside the materials, you already have an example of how to test an ISA instruction being implemented. Yeah, and that's essentially how you do it. We focused on RISC-V. Of course, there are different ISAs that use different templates and obviously different decoding operations, but this is essentially it. That is the last piece of content I had on my slide.